So, last time we were making reductions. So, we have started with let us see what all things we made. Click, right, and from the click we showed that regular click is hard, right, by giving a reduction. Then we also showed that what is called multicolored click is hard, right, when we had a partition of vertex sets and you wanted to pick one vertex from each of this click. Okay. So, regular click, multicolored click, and in the beginning we had shown a reduction to independent set, right. Just take the complement of each other. Okay. Now, does all these things also will hold? Does, if you take a complement of regular click, what will you get? Is a complement of regular graph regular? No. Yeah. So, can you give an example? Even then, my point is very question. Let G be a regular graph, then does it imply that G bar is also regular? That is all that I am asking. A lot of people look very confused. So, degree is n minus 1 minus t, right? Because what is its complement, right? You have an edge to every other vertex which you do not have edge in the previous graph, right. So, if you were neighbor to d people, because the number of vertices has not changed, your what is this will be? So, if you are regular here with d, now you will be regular here with n minus 1 minus t, right. So, that implies that if regular click is W1 hard, then so is regular independent set. What about multicolored click? So, like, can we have a version of multicolor independent set, right? So, the multicolor independent set, multicolor independent set is going to be that you want, you are given a partition into V1 to V2 Vk, they are independent or whatever, does not matter, and you need to pick an independent set containing precisely one vertex from each. Okay. Have an independent set with one vertex from each class, one vertex from each class. Is this hard? We have this. So, can we define a multicolored version of independent set and say this also is hard? Okay. But if I take a complete graph, I start with this, some things will become click, then what should we do? An instance of multicolored click, if you recall, is V1 Vk, right? It is a partition of vertex set, right. So, if I take a complement of this, right, of course, the edges here will get complemented, plus you will also be able to get that these are click. What should you do now? But if you are looking for an independent set containing one vertex from each, does it matter? I take its complement and then I take a complement and remove all the edges in a class. Okay, so you delete this, 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 right? And now you can show that, like, if you had a k size independent set in this graph, definitely they corresponds to k size click in my original graph in the partition graph. And if you have a k size click in the old graph, it will correspond to k size independent set in this graph. So you can do this small trickery and prove some of these things. Okay. So this implies that multicolor independent set is also hard. Is hard. Okay. Okay. Let's see. Now here's a problem that I would like to show is hard. Okay, let's see if you are able to. So this is what is called Max-Vertex cover. Okay. Input is G, K, and T. Okay. Input is G, K, and T. My parameter is K, and my question is, does G has a set S, right? Cardinality of S is at most K, and number of edges that are incident to S is at least T. Right. Now, if T equal to number of edges in the graph, then what is this problem? It's the same as vertex cover, right? You are looking for a k size set, so that the number of edges that are incident to that is m, right? So this is a generalization of vertex cover. So now I am asking you, I give you k vertices. Try to cover as many edges as possible with these k vertices. Okay. Is it hard? Is it easy? Suppose I tell you hard, okay. Now I ask you, the first important thing is, what is the right problem to, like, why it is hard? Ask yourself a question, why this problem is hard, and like what makes the problem hard, why your obvious strategies do not work, and how can you encode those obvious strategies using some right starting point for your reduction, right? So what is hard here? Like, what will be the most obvious way to design this algorithm? Forget about even NP hardness. Why it is not, like, if I wanted to try a polytime algorithm, what will I do? No, like, what do you mean take T edges?
Choose one edge up to T, like, and take one vertex from that.
I mean, then you are bound to pick more as a function of T than K.
So we will be trying to pick k vertices greedily such that maximum, like the one that has maximum integral.
Okay. So what happens if I pick a vertex of highest degree? Okay, I pick up a vertex of highest degree. Or rather, let us sort the vertices of high degree. Sort the vertices let's sort the vertices with respect to degree. It's like V1, V2, Vn, and what is the property? dV1 is dV2 greater than or equal to dVn. Can you tell me what is the maximum number of edges any k vertex can cover? Forget about t or not. I am asking what is the upper bound, like immediate upper bound can you come up with? He said, look, any k vertex can never cover more than these edges.
K times dV1.
So one bound is what she says, look, you can't cover more than, so t better be upper bounded by k times dV1, because dV1. Anything else can you say? That is dV1 is maximum degree. Anything else? Sum over t is also upper bounded by summation time dvi I equal to 1 to k, right? I mean, you look, this is your top vertex, you can cover something, you can cover something, you can cover something. Okay. Now ask yourself, which situation can I have such that I will t is exactly equal to, when will this happen? When will this happen? Huh? If they are independent set. So the difficulty is that this may not be, the top k guys may not be an independent set. So does it tell you where to start from? What to encode? You understand my point? So you just now told, the only reason we are going to lose anything less than t is because the top k vertices may not be an independent set among themselves, right? So now it appears that maybe we can use this algorithm, like if there is a good algorithm for this problem, we might be able to solve somehow independent set, right? So look at, because that is like what I want to set t in a way that, look, you have no choice but to look for an independent set, otherwise you can't achieve that, right? So at least that starts to ring a bell that maybe independent, if at all this is hard, then independent set is the right problem to show hardness. Okay? Now what should we do? Right? So happens when V1, V2, Vk an independent set.
Given an instance of independent set, you make it regular, then they all.
We have this, no?
Yeah,
Right? So now this is exactly what I said. Like if you start thinking, like then you start to need some of these things, and this is why people, I mean, why on earth people will go and show regular independent set is hard? Because for some of the situation you want some of these things. So these are like intermediate problem that crop up while trying to show reduction. Then you first show that is hard, and then you make a systematic reduction starting from those problems. Okay? So Pratik's suggestion is, let's try from regular independent set. So what he wants to do is to show from regular independent set parameterized reduction to Max-Vertex cover. Okay, so let's do that. So what are we given for regular independent set? A GK, every vertex in V of G has degree equal to R. So everybody is saying that okay, take instance G, K, Kr, right? Okay. Now, what implies if G has an independent set, so we have to show this is if and only if, right? So, if G has an independent set, say I of size k, then what is the property of this? This is I, there is no edge, right? And so, all the edges which are incident to this vertex are, because this is a regular graph, is going like this. Okay? Right? So, definitely total number of edges that are incident on these k vertices is kr. Okay? So, this is perfectly fine. What about the reverse direction? All right? So, reverse direction, suppose, is that fine? Okay. So, you have a set, say S in G, such that it covers how many edges? It covers T equal to kr edges. Okay. Now, you have to show that why it is an independent set. So, suppose if you had an edge here, what will happen? Then if you have any edge, then this edge is going to be counted twice, right. So, then the total number of distinct edges that you can cover is at most kr minus 1, right. So, if there is any edge in F, there is any edge in S, then the number, total number of edges that we can cover is at most kr minus 1. Is that fine? Because no vertex can cover more than r edges, right? No vertex can cover, and there is an edge that is covered by 2 people. So, the count of that edge will decrease from the total sum, right. So, this implies that S is an independent set. So, basically notice that this problem is this. Okay. Okay. Is it fine? Is the reduction fine? Okay. There is not much happening. Okay. But now I want to change something. Okay. And then I want to show you that, suppose I wanted to show that this input G is bipartite. Is bipartite. Not only it's like it's a bipartite graph, and I want to do the same thing. Now, the problem is what happens? Can I start with this reduction? Can I start with an independent set reduction where I take regular independent set in bipartite graph and all this kind of thing? Can I start with an instance of bipartite graph in the left hand side? Because if I could start in the left hand side a bipartite graph, nothing will change, no? But that problem is poly time solvable, right? So, what does it mean? Then that is the time when you say, does it imply that the problem which are reduced to also inherits the complexity like bipartite graph, or it inherit complexity like general graph? So, you get my point. Okay. So, it is not trivial, but it is difficult. It's not difficult, but it's not an easy, but you can still show that the problem is NP hard on bipartite graph. Okay. So, all I can show is NP hard. So, then you need to come up with a different starting point of the reduction, everything, and definitely this wouldn't follow. Okay. So, but now I can still ask, because but this reduction showed that the problem is W1 hard, right? Problem is W1 hard. Does it imply that even in bipartite graph the problem is W1 hard, or it becomes, yeah, I agree that because of your difficult hard NP hardness reduction, the problem is NP hard, but that doesn't imply, that may not imply that the problem is W1 hard, right? Because the reduction may be taking k to be some function of input size and everything, and okay. So, what we will show in a minute. Okay, so, what is known is that problem is NP complete on bipartite graph. Okay, so this is known. Okay. Now my question is, what do you think is the status of this problem on bipartite graph? Okay. Okay, so before we go to bipartite graph, do you think this problem is FPT parameterized by say k plus t? What about parameter k plus t? No, just general graph, but now I have changed my parameter. I am allowing you two things. I am asking you to come up with an algorithm whose running time can be governed by the size of the set and the number of objects that it covers. Before I was asking you that give me an algorithm that just governed by the size of the set, not the number of objects that it covers. But now I have changed the parameter. I said, look, no problem with k. You just now show the problem is hard. Does it imply that the problem is also hard with the parameter k and t? Or can I come up with an algorithm where I can write down the running time of the algorithm in the form of k and t? Why t is a function of k?
It is hard in regular graphs.
Regular doesn't mean that r is like constant. Regular just means every vertex has the same degree. Why? Root n regular graph doesn't exist. Click is an n minus 1 regular graph, right? So, what do you mean by function of k? This I didn't get it. Look, a single vertex in the click can cover n minus 1 edges. So, it's like 1 and n. So, t has nothing to do with the what do you call as a function of k. Like click, one vertex can cover n minus 1 edges. Okay. Okay, so here is suppose this is a vertex, and suppose what happens if are we done? If the highest degree of vertex is at least a, pick that vertex, you are done. So, what you know then? Maximum degree of graph is upper bounded by t minus 1. Okay. Does it help? Okay. More help. Suppose this is the highest degree vertex V1. and this is neighborhood of V1. And suppose S intersection closed neighborhood of V1 is empty. What can you say? What can you do then? If what happens if I have S intersection n of V1 is empty? It doesn't intersect either V1 or not, or any of its neighbors. Then what can I do? Delete some vertex x and add V1. Do you cover more? See, if you are covering at least t guys before, you deleted some vertex, right? But when you add V1, because none of its neighbors are there, when you add V1, you will add these edges are newly added edges, right? And if this vertex has degree, maximum degree, then you will be covering more only. You will not be covering less, right? So all I am trying to prove is the following. This is my lemma. Okay, there exists an optimum solution S such that S intersection closed neighborhood of V1 is not equal to empty. Here V1 is the vertex of maximum degree. Is that fine? Why? Because here is the argument. Suppose V1 and none of its neighbors are there, then is empty, then you just throw any vertex out of S, right? Then you definitely have not thrown up V1 and any of these guys, right? It doesn't matter because they are just not there, right? And then you introduced V1. So the moment you will introduce V1, right, you will be covering that many number of edges. So when you delete X, you might have lost out on some number of edges. But when you introduce V1, you have introduced many more new edges because these edges were not counted before because these vertices were not part of my solution. Okay, is the argument fine? Pratik, you look a bit confused. So what is an algorithm now? Yes, you start on, now I know, now I have got a set, right, from where one of the vertex must go into the solution, right. So I decide branch, right, I delete this vertex, look at the total number of edges that are covered, I delete that from my bound and I recursively try to solve the problem. Okay. So what's my algorithm? Algorithm is very simple. Algorithm is basically that's it, not this to the power k, right. So suppose I decided, oh, look at the branch where V1 is going. So now what I will do, G minus V1, k minus 1 and t minus degree of V. That's it. So this is my branching vector, right. And in the next one, again this statement is true, right. I can branch because by deleting a vertex, I cannot make my maximum degree increase, right. So what is the running time of this algorithm? T to the power k. Okay. So the running time is, if you notice, what is the running time? Is t comma k comma t is at most t times t k minus 1 comma some t prime where t prime is less than or equal to t. I don't even care, but I know that this is like, so this is upper bounded by t power k, right. That's it. So I mean, so the problem, the complexity of the problem, hard or easy, is always with respect to what is the parameter we are trying to do, okay. Not with respect to, when I say hard, hard doesn't mean that I cannot design an algorithm for this problem, right. I have to specify it is hard with respect to what, because then I am saying I cannot design an algorithm for this problem where the running time is of the form following. Okay, excellent. So we got this algorithm, okay. So we also have t power k algorithm for this problem. Okay, now let's go back to our bipartite graph. So now no more T. We will use this algorithm in a minute. Okay? Okay. What do you think? Huh? Yes, that's true. But why? No, no, no. We will use this algorithm for very different purpose. Not yet. Like it has nothing. We will use this algorithm to do something very different. This requires very different algorithm. But imagine yourself that, like, what is the basic thought? If there are k objects that covers t things, then there should be at least one vertex which should cover how many things? Huh? T by k things, no? Is that okay? Like pigeonhole principle. So let's call this high. What is my high? All those vertices such that degree of those vertices is greater than or equal to, right? So any optimum solution intersection with H must be none. If there exists a solution which, if there is a set of k vertices that covers at least t edges, then that set must intersect with my high degree vertices. Do you agree? Okay. So what is the meaning of this? So and this is true about general graph, not about just bipartite graph. It is true about any general graph. Okay. So what we showed is that if there exists a solution S, then H intersection S is at least 1. I am not saying how many. Okay. Now what can you do? Okay, now I am telling you that there are cases where you can run this algorithm. In which case can I run this algorithm? This algorithm. Suppose H is more than 2k, then what can you say? Cardinality of H is more than 2k. So what is my bipartite? What is my input graph? It's a bipartite graph, right? So there's a bipartition, right? There's an independent set here, there's an independent set here. So now, if look at this H, then H is some portion here, some portion here. By pigeonhole principle, at least one of those guys has size more than k, right? If they have, now each of them are independent, each of them covers at least t by k edges. So how many edges did they cover? K edges. We are done. Okay. So what did we learn? So this is why I said this is, in this case we can find k vertices of very high degree which are independent, and hence together they are able to cover t edges. So it's like a polytype, right? Okay. So if cardinality of H is more than 2k, okay, I still want to keep this algorithm, so I will keep it, but now I will, okay, now also I can't do this, so I will rub this, okay, remember this algorithm, okay. So what happens? So it says, what we are saying that if more than 2k, then there exists a set S, there exists a set X subset of H. X is an independent set, and mod X equal to k. That's all that I am saying, right? If my number of high degree vertices is at least 2k, by pigeonhole principle, at least one of the part must be more than k, right? So if this is my bipartition A comma B, right? So imply why? So the proof is very simple, okay? Since 2k, either H intersection A is greater than or equal to k, or H intersection B is greater than or equal to K. Okay? So, let X be a set in either A or B where H intersection A is greater than K. Okay, say without loss of generality, say H intersection A is greater than or equal to. Set, let X be a set of size K in H intersection A. That's it. Okay. Now, what is the property of this set X? This is an independent set, and what is its degree? Each of them cover how many edges? Even if they are adjacent, outside, it does not matter because they are covering different edges, right. So, this implies number of edges that are covered, okay, this is number of edges covered by X is at least T over K times K, which is greater than or equal to K. Done. Okay. So, once this lemma is there, now are we done? We just now showed that at least every solution must intersect at least one, right? And if they are too large, we already have an obvious solution. Otherwise, it is too small. What is a small, right? So, if I cannot do this, it means cardinality of H is less than 2K. So, what is the running time of this algorithm? Done. Now, I can do a branching algorithm on H, right? I know one of the vertex must go in the solution. So, I decide which vertex goes into the solution, delete him, set my appropriate. So, for all V in H, what I will do? What are the instance I will make? G minus V, right? K minus 1 and T minus degree of V. That is it. So, this is recursively I will call this. So, the running time of this algorithm is governed by T of K less than or equal to 2K times T of K minus 1, which is 2K to the power K. And it is nothing about bipartite graph. Any graph which has a small coloring number, right, then I can do the same thing. Like then I have to just say, oh, not 2K. If the graph was say for a planar graph, it is 4 colorable, right. So, I have to use the term 4K because then, oh, by pigeonhole principle, at least in one color class, there is independent set of size at least K done. Otherwise, I will do with this. Okay. I mean, you can do many things. So, like, okay. Is that fine? Now, we have started to use whatever we learned. Okay. 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 So, now, okay, fine. So, we realize that max K vertex cover is hard on general graph. Okay. So, then people ask, okay, fine, can you do some sort of approximation in FPT time? Okay. And what I mean by approximation, so let me write it down explicitly. Okay. Okay, now I will rub this. Okay. It's hardware. And anyway, I don't think I probably need it, so I will rub it. Okay. Then we will go back to making reductions. Okay. Okay. So, now what I am interested in. Okay. So, suppose I am interested in alpha factor approximation. So, what I mean by this? Okay. So, you can either tell me that look, so what should be the outcome? Either say that there is no set S that covers, there is no set S of size K that covers at least T edges, okay, or find a set S such that the number of edges covered by S is at least alpha times T. Now, what it should be alpha here? 1 less than 1 what? right, because it's a maximization problem. So you want to cover that much, I'm not able to cover that much, but I'm able to cover some fraction of it, okay, like half fraction I'm able to cover, or 1/3 fraction I'm able to cover, okay. Okay. So can we design such an algorithm? So can we design this for alpha equal to half? Okay. So let's try to design an algorithm for alpha equal to half. You get my point? Okay. So the first question which I want to ask, when, okay, so my question to you is, when S being V1, V2, Vk is a factor, when S being V1 to Vk covers at least T by 2 edges. When? Or rather, can you tell me a situation when you can say, look, you can never cover T edges? This is one question, okay. Another question that I want to ask, answers are all on the board, okay. In which situation we can say that there is no S covering at least T edges.
So that we can conclude from some factor approximation for independent set of edges.
There is no independent set approximation in the world.
Every vertex has degree strictly less than T by K.
I asked you to cover too much. When can you conclude that I asked you to cover too much?
Sum of the top three degrees is greater than less than t.
If the sum of the top degree is less than T, then can you really cover more than K edges? I mean, even after counting, I cannot cover more than this edges, right? So then, like even after over counting, I cannot cover more than T edges. How on earth do you expect me to cover more than T edges? Okay. So the one question is, definitely the answer for this we can say, when okay. So this, if this situation happens, then you can definitely say that you are not covering. Okay. So if this situation did not happen, okay, so this is, so now I am asking you, so can you upper bound, how many edges can you cover anyway? How much over counting we have anyway? How many edges can be over counted? If I ask my potential solution, this is my potential solution. If I say, look, this is okay, it's greater than or equal to T. What, rather let's say,
Counted every edge twice
hmm?
in this summation.
Yeah, so how many edges will you count twice? how many edges will you count? At most, how many edges can I count twice in the top k, guys? Which edges are you counting twice? Which edges are counted twice? How many edges are there? So at most, I can count that many edges, right? So top k, guys, covers at least how many edges does it covers distinctly? Cover. Okay. So let's use the word cover. Okay. So cover of top k, guys, is how much? At least how much it covers? Cover of S, like this is summation of degree. I am not talking about summation of degree anymore. I am saying how many actually new edges does it cover? Do you have a lower bound on that? Their total summation degree is t, out of which some of the edges are counted. How many of them are counted twice? So then what is this number? Look, they are covering that many. Now I want to subtract all those edges which are counted twice. How many edges are counted twice? Exactly, precisely those edges which have both endpoints in S, but S has size k. So this is k choose 2. Okay. Now I am asking you, when is this a factor half solution? In which situation can you say this is a factor half approximation? Yeah, so let's say this is at least t minus k square, just to make my life. So I want to say, look, boss, t minus k square is greater than or equal to t by 2. When can I say this? This is like if it is a factor half approximation, I want to guarantee. When, in which situation can I say that, look at the top k vertices, okay? They definitely cover t minus k square edges. If t was way larger than k square, I mean, if t is much larger than k square, then it should be an approximation. So basically what I want, t minus k square should at least be t over 2, which implies t should be at least 2 times k square. So if t is at least 2 times k square, then this is a factor half approximation. Otherwise t is at how much? Less than? Then do we have an algorithm? We had t power k algorithm, no? So now in this situation, I can actually check whether such an object exists or not by running my t power k algorithm. Do you understand my point or not? Okay, so what happened? Okay, so we just try to analyze these things. Okay, so there are two things we are saying. Okay, we are saying that top k vertices cover is a very good candidate for my solution. Okay, when it is a good candidate solution, if this k square people that I needed to, that it overcounts, okay, if the number of edges that I really needed to cover is too large compared to this k square quantity, then this itself is a good approximation. If this does not happen, then the number of edges that I need to cover is now number of edges that I needed to cover and the set size are function of each other. And then even if I had an algorithm where t power k algorithm, in that situation I can apply that algorithm and be done with it. Okay. So now we'll write down this algorithm here.
Don't we have a FPT for infinite, like FPT approximation? No?
can't have. Or it shouldn't have.
I mean, so approximation for independent set is an open question, like not like it will contradict some hypothesis if I'm not.
It will.
Even it cannot be approximated within any factor, is that?
No, it cannot be approximated any factor, even in FPT time. There are, like, I mean, okay, we need to assume slightly stronger assumptions, like we don't know how to show that unless FPT not equal to something, but we know how to show that more or less, at least constant factor we can show without, like, just with FPT not equal to W1. But if I assume ETH or slightly gap version of ETH, then we can show that you cannot have anything. Okay. And so now I told you both situations. So let's write down the whole algorithm properly. Okay. Okay. And then, okay. So what happened? So the algorithm is fairly simple, right? What did algorithm did? First situation. Okay. What is the first situation? This if summation of dvi, okay, minus k square is greater than equal to t by 2, okay, is greater than equal to t by 2, or okay, yeah, if it is greater than equal to t by 2, then what did we say? Return s equal to v1 to vk, right? That's a factor half approximation, because, and we can count this. This is the poly time. We can count this. Okay. Else what happens? Summation of degree vi minus k square is less than equal to t by 2. And okay, so there is a 0th step, right? If summation of tvi is less than t, say no, right? So this also we have a step, 0th step. If even after over counting we can't cover t edges, then forget it. So then we do this, then we do this. Then what do we know? This is less than this. So basically what it means that this is less than equal to t minus k square, which is less than equal to t by 2. That implies what did we get? That t is at most 2k square. Okay. In this case, what did we say? Run t to the power k algorithm. So now what is t? 2k square. So this is 2k square to the power k. So it is 2 to the power big O of k log k. So we can get a factor half approximation for this problem. Alpha equal to half, we can get it in FPT time. But like, suppose I wanted to get closer to 1. Like, tell me another number which is closer to 1. Say 3/4. What will change here? Say alpha equal to, or let's say, let's choose alpha equal to whatever you say x by x plus 1. Some x by x plus 1, right? Like, so I want to get that much closer to this x by x plus 1. So let's see what we can say then. Now, what will my algorithm change? First, this remains the same, right? Now, next case will what? This will be, if this is greater than equal to, what is my factor now? So my factor is x by x plus 1 times t. So x by x plus 1 time t. So what is t now? Can you tell me? So now we have t minus k square is xt by x plus 1. So, this is what? So, this is x plus 1 by t minus xt by x plus 1 is less than equal to k square. Is that fine? Or I am doing something not right? No, this is fine, no? So, what do I get? X t by, is this correct? Is this correct? So, t is x plus 1 to the power k square. Okay, excellent. But now, in this case, we can run our algorithm again. So, now, what is the running time in this case? Is going to be x plus 1, whatever that x plus 1 is, to the power k time k 2k. Is that fine? This is my running time. So, till x is any constant, I am very happy. So, what could be the best algorithm that we could think of? You say, look, I give you an epsilon, you give me an algorithm. So, the best algorithm will be that I give you an epsilon, user gives me an epsilon, and what should I return? And it covers at least, and objective is to cover find S. Okay, so let's say now if I substitute alpha, either this or covers at least how many edges? 1 minus epsilon times t edges. Okay, this is what it is. Now, we should be able to get something from here, no? So, what we want? X by x plus 1 should be greater than or equal to 1 over epsilon, right? So, what is this? This is x is greater than or equal to x minus epsilon x plus 1 minus epsilon. Is that fine? So, what do we get? Epsilon times x is greater than or equal to 1 minus epsilon. So, what is x? So, you apply this algorithm with this value of x. Right? Which is definitely greater than or equal to 1 over epsilon. Okay. So, what did we get? We get for this problem, what did we get? We get an algorithm running in time. What is the running time of our algorithm? This is poly time, so let us not worry about it. So, the running time of this algorithm is k times 2k is sitting there, and what it was? X by, no, oh, it was x plus 1 to the power k. Now, what is this algorithm then? X is like 1 minus, so it is 1 by epsilon plus 1, right? Oh, right. Minus 1 plus 1 k to the power 2k. So, what are we getting? We are getting 1 by epsilon to the power k, k power 2k. What? Fix x equal to that. No, you gave me epsilon, fix x equal to this. Why you want to apply for different value? You just, all you want is that I want 1 minus epsilon. It's your choice to choose x. You choose any x greater than or equal to this, suffice it. So, I will choose which is smallest, no? So, I will choose this, exactly this, right. So, what did we get? We get an algorithm with running time this. Okay. Okay. Now, this is like so, this is the algorithm, right, whatever we design, but we can come up with an algorithm which does the following. Okay. So, it can answer So, I gave you this algorithm, but there are algorithms which can do, we can solve 1 minus epsilon times t in time. That's it. So, we can get rid of this, like this is not required, but it requires different algorithm. Okay. We will do someday, not now. Okay. Any question? Right? Because look, notice, because the problem is hard, you need to have a dependence on epsilon, because you can't if this does not depend, then you have shown that the problem is FPT, right? So, you need to have an additional parameter, like what was our additional parameter? It was t, but we could also use quality of approximation as our additional parameter, right? Now, what I am saying, closer to best solution you are going to get, more and more time you are going to consume, right? And this is the whole idea about, if you learn in polynomial time approximation schemes, means like there is a factor 2 approximation, but maybe for vertex cover you have a factor 2 approximation, but you wanted to find a solution which is like 1 plus epsilon times k, like k plus, like much smaller, then how much time it will take, right? It starts to take time which depends on the epsilon. Okay. So, these kind of algorithms are called polynomial time approximation scheme, and there are different kind. Is this epsilon sitting on the input size on the top, or it is sitting like an FPT below? So, if it is sitting like FPT below, it is called efficient polynomial time approximation schemes, okay? And if it sits on this, then this is just normal pitas. Okay? So, people play. So, is this optimal or is that optimal? Like, is n to the power f of 1 over epsilon is the best possible, or we can get f of 1 over epsilon and n to the power cube kind of algorithm. Okay. Now, I can also start, what is the form of f of 1 over epsilon? Is it 2 to the power big of 1 over epsilon, or is it 2 to the power big of 1 over epsilon square? I can prove, is like I can prove up to all this asymptotically in here and there. Okay. So, that is my goal, to show you some of these reductions. Okay. Is this fine? Then we will move to something different. Okay. I don't have, I don't want to tell, I mean, I can tell you this, but it's like, it's mouthful. Okay. Not for the class. I mean, if someone is interested, I can tell you in private, like a non-recorded version. Okay. So, now I will move to another question that has dominated the parameterized complexity quite a lot, which I never talked about, is dominating set. Okay. Now, I want to show that dominating set is also hard. Okay. So, let's first let's see what dominating set means. We can also make similar kind of approximation, when that can happen, when that cannot happen, and we will look over it. Okay. So, okay. So, now we will do dominating set. Okay. So, what is the dominating set problem? So, your input is graph G K. This problem also appeared last time when we were trying to show this bipartite business. Okay. My parameter is K. Okay. And question is, does G has a dominating set of size at most k, dominating set S of size at most k. And what is this? Basically, it means closed neighborhood of, say, S equal to vertex set of G. right? Or in other words, for every vertex in my graph, either the vertex belongs to the set S or one of its neighbors belong to the set. And what reduction we have shown last time, that if dominating set is W1 hard on general graph, then it is W1 hard on, if it is hard on general graph, then it is hard on bipartite graph. Okay, so this reduction we have. Okay, so if dominating set is hard on general graphs, implies dominating set is hard on bipartite graphs. This much we know. So let's try to do the, let's fill the gap we have here. Okay. Which problem is looks like in dominating set? Are maximal independent set dominating sets? Independent set that cannot be extended further, are they dominating set? Why? Or why I am not able to extend? Because for every vertex there is some neighbor that is sitting here, right? So every maximal independent set is also a dominating set, but not other way around. Okay. So for dominating set, can we make any algorithm for with respect to any parameter that you can think of? There are input sizes also, you can try them. It is n. Can you make any algorithm which finds a dominating set of size at most k? Any algorithm? Any. Okay, no, but yeah, so tell me, what is a brute force algorithm for this? No, first let parameter k. What can you do? N choose k. Okay. So next two lectures, this is the algorithm, right? N choose k. We will show that this is all that you can do. Okay. So our objective will be to show that if you wanted to find a k size set which is a dominating set, then this is our algorithm, and this is the only algorithm probably we know of. Okay. So and this I will, so this is, what is this running time? This is like n to the power k, right? So I will not show to you that it is, oh, n to the power little of k is impossible. This also not I will show you. I will literally show to you that you cannot probably do k minus epsilon. You get my point? Like you cannot even get k minus 1 kind of algorithm, or even like k minus 1/4 kind of algorithm. Okay? So we will get there. This is why we have defined all those ETH, set in the first class, so that we can use them up to our choices. Okay, but besides that, so this is that hard question. Okay, for independent set we can't search at reductions. Okay, okay, but for we have an n choose k algorithm, which is like, and then you can check whether that forms a dominating set or not. So it is like k plus big of 1. Okay, but now can you come up with an like? But does this imply that it is FPT parameterized by n? This algorithm? N number of vertices. Okay. Why? Fine. Okay. And this exists. Okay. Is that fine? Like I'm happy if you give me 1.99 to the power, and this exists. This is really a question. It is not like I'm not trying to go and search. No, it exists. I mean, if I had time, I can tell you on the board itself. This is not something which is okay. Generally, I give this an exam. So
Same like that we did for vertex cover, lower degree graphs that we designed.
what? Try. Okay. As I tell you, this I give in my exam. So this is like my exam question. So how can I tell you my exam question? Answer. Okay. But anyway, so now I want to show that at least let's start with showing that for this problem there is no f of k n to the power big of 1 algorithm. This is the first thing which I want to show. Then I want to show that this does not even have n to the power little of k algorithm, and then I want to reach that it actually cannot even have this kind of algorithm. Okay. So first let's start from here. Okay. We want to give a reduction from independent set, and now we will start to see the value of this multicolored version of. I don't expect you to come up with this reduction. It is slightly all over the place. Okay. So I'm going to start from multicolor independent set. So what is my input? My input is V1, V2, Vk, and you want to find vertex from each that forms an independent set. Okay. Now I want to transform this into a dominating set instance. How should I go about it? So if I want to simulate independent set, let's think about it. What is my independent set solution? You're going to pick one vertex from each of these guys, right? So somehow I need my dominating set. Think of the reverse direction, right? Dominating set must pick something from each of these guys in the reverse direction. How can I ensure that dominating set picks one vertex from here? What is the smallest object that you can think of that will imply that these guys will pick? And that's very easy. Okay. Here is my Vi. Let me do with respect to one Vi. What I'm going to do first, make it a click. Okay, make it a click. Now I want to ensure that you at least pick one vertex from here. So what I will do is that I will add two vertex, say x and yi, which is adjacent to everything. Now what happens? This xi and yi is neighbors are here only. So either you have to pick xi, or you have to pick yi, or you have to pick a vertex from here. So this we have ensure. But the moment I will set up my budget, which will imply that you can't pick up these two guys, you will have to pick one from here. Okay. So what is this? So suppose I set up my budget as k equal to 1. So suppose this is like g comma k. My new budget for dominating set is also going to be k. Now what happens? Now if it is k, now from each of them you have to pick one dominating set vertices, right? So either you can pick xi or yi, or you have to pick one vertex from here. Right? So there is absolutely no point picking x, because you can only pick one vertex. So if you pick xi, you can't pick anything on this, right? You don't have budget for this, right? But then who will dominate yi, or who will dominate these guys? Maybe these guys can be dominated from outside, but if you pick xi in your solution, can you dominate yi? Because you cannot pick anything anymore here, because from each of the class you have guards sitting on them. Right? So this is what we did. So this is great. Okay. So now we have. So now if started with this gadget, I have started with this gadget. Definitely, if I start with k size independent set, I have k size dominating set for my graph. I'm not talking about edges. This is my whole construction. At this point of time, this is what my construction is. That for each Vi, I have made into click and I have added this. Now, it says if you give me a k size independent set, then I definitely have k size dominating set. Forward direction is fine, right? Is that okay? That's it. So I have, what is my graph? Graph is just disjoint union of click and two vertices like this. This is what it is everywhere. So definitely if I start with k size independent set, What is the problem? If I start to going in the reverse direction, there is absolutely no guarantee that if you give me k dominating set here, they will be independent. So somehow I have to encode the adjacency relation between them. Is that fine? I have to encode adjacency. Means if I pick a vertex here and I pick a vertex in some other class, so let's pick up some, so suppose this is Vi, okay, and let's draw a Vj, okay, here the Xj, Yj, okay. Now suppose I picked up a vertex, say suppose I picked up a vertex A here and I picked up a vertex B here, right? I want to somehow, I think, look, if you picked up these two vertices, then somehow they must form an independent set, right? That is my whole goal, right? So how can I ensure this? So what I do is that I make a vertex WAB for an edge between AB for every, and whom should I make him adjacent to? No. I make him adjacent to everybody but A. I make him adjacent to everybody but B. Now what happens? If now if I go back and I looked at the edge, looked at AB. Now if you had an edge between them, then there is a WAB which is adjacent to everybody else but A, which is adjacent to everybody else but B. Who will dominate him? Right? So I have encoded adjacencies by non-adjacencies. You understand what I did? Right? So what? For every edge AB in G, what I add WAB and make him adjacent to what is that called? Suppose it belongs to Vi minus A and Vj minus B. That's it. So that's the end of your construction. Now, I mean, you can show that. So forward direction is still fine, right? Forward direction is why still fine? Why forward direction is fine now? We have added far too many vertices. But if you pick up k size independent set here, now look at any edge vertex, right? It's an independent set. So not both of its endpoints is there. So at least one of them is from here, so you would have covered. We'll do it more details next time, but that's the end of the construction. Okay, I need 10-15 minutes more, which I don't have, but like this is the end of the construction. So try to, like, starting from here, this is the full construction. Try to, like, what is that called? Complete the proof yourself. This is, right, it's not more harder than this. Okay, so what we did, we started with V1 to Vk. We ensured that you at least pick one vertex from here by making it click and adding two guard vertices. Okay, now to what do you call? Pick up my adjacency. For every edge, I added a vertex and made him adjacent to every vertex but to A and but to B in two of the classes. And that's it. So you try to prove formally, you will be able to see this. Okay. Any question? Unfortunately, I have a meeting at 11. I don't know what time is this. Oh, it's 11. Oh, this is correct now. So until you have a question, at least I'm done.